Okay, so the answers to this question: write a similarity statement comparing the three triangles. You can, if you want to, you do not have to, but you can redraw these triangles. And if I redraw them, yes, I know, I'm such a great artist. I'm always going to put the right angle in this corner. You could do it however you want to do it. It's no big deal. So comparing the big triangle, J is here, and I'll put, let's see, uh, this one's a little bit shorter. Okay, and all my other triangles. Okay, so this one side's a little bit shorter than this one. So this will be L, and this will be K. All right. So if you compare this second big triangle, in this second big triangle, M is the right angle, and KJ is the hypotenuse, and JM is the shorter side. And then in this smaller triangle, I'll call this triangle number 1. So this is triangle number 2, this is triangle number 1, and this is the big triangle. Let's see. M again is the right angle, and LM is the shorter side, and LJ is the hypotenuse. So now I can definitely see that triangle KLJ. So I went to this one, to this one, to this one, to the right angle. Is going to be similar to triangle KJM. Is going to be similar to triangle JLM. All right, so we need to know how to compare the three triangles, and this is really important because we're going to smush the similarities with the geometric means. So this is the big triangle, and all I did was I redrew the triangles like we were just doing, and I gave this perpendicular line a name called H. I called this the regular sides A, B, and C because we're used to doing Pythagorean theorem. This is an alternative to Pythagorean theorem. Okay, so this is a shortcut, if you will, and this, again, only works if H is a perpendicular line. If H isn't a perpendicular line, you cannot do it. It's not going to work. Okay, so we redrew the triangles. They're similar. This is the second triangle. This is number 2, and this is the first triangle, number 1. Okay, and this is the big triangle, A, B, and C. And as you can see, I just redrew the triangles like we did previously. So now that we have all three triangles, redrawn, and I told you they're similar by angle, we can now compare the sides and create proportions because their sides have to be proportional. So if you look, B over A has to be similar to y over h, and h over x. So I compared the two legs of all the triangles. Okay, so this works because of angle-angle similarity. The triangles are similar and the sides are proportional. Same if I compare the hypotenuse, C, with the shorter leg, A. So C over A has to be similar to B over H. B over H has to be similar to A over X. So again, this is another set of proportional sides that will work. Then the last one, let's compare the hypotenuse C to the longer leg B. So we have C over B is similar to B over Y is similar to A over H. So here's another set of proportional sides. These three triangles are similar, so these three proportional statements are accurate. Now, if you notice something that happens here, here's H and here's H. That is a geometric mean. Ignore this for a second. All right, if you look at this proportional statement, here's A and here's A. They're on opposite sides. That's a geometric mean. Get rid of this statement for a second. And same thing over here. Oh my gosh, here's B and here's B. They're opposite of each other. This is another geometric mean. Remember, a geometric mean is when it's like x equals x over 4. And all you have to do is cross multiply. The x's are across from each other, just like the h's, just like the a's, just like the b's. So we can create an equation here for using geometric means. If we cross multiply, we're going to have h squared equals x times y. Now what that means is every single time that this is a perpendicular line, this proportional line squared is going to equal x times y, the two parts of the hypotenuse. So looking at this one, a squared, if we cross multiply, equals c times x. So that means every single time this leg is going to equal squared. This leg squared is going to equal this part of the hypotenuse times the whole hypotenuse, c times x. So again, this leg equals this part, the part closest to it, of the hypotenuse times the whole hypotenuse. So probably the same thing is going to be true of the other leg. B squared is going to equal this part of the hypotenuse, y, times the whole hypotenuse, c. And let's see if that's correct. B times b is b squared, c times y. Oh my gosh. B is the whole hypotenuse, y is the part of the hypotenuse. So these are 3 shortcuts to this problem, and it's written in your book right here. And guess what it's called? Geometric means. Okay, so this is geometric means in similar right triangles. So h squared equals x times y. H squared equals the 2 parts of the hypotenuse. A squared equals this part of the hypotenuse closest to it times c. B squared equals this part of the hypotenuse times c. These are shortcuts to Pythagorean theorem. So some questions, it's going to be confusing, but once you get the hang of it, it's really awesome. And if you forget, you can still do Pythagorean theorem for the most part. Okay? So find x, y, and z. All right, so again, our shortcuts are h squared equals x times y. A squared equals c times x, and b squared equals c times y. Okay, so in this case, h is x. This part, and these x's and these y's are probably going to confuse you. But remember, this is the part of the hypotenuse closest to it. This is the part of the hypotenuse closest to b. Okay, so looking at this one, there's lots of ways you can get this started. Maybe. Sometimes there will be. But if you look at this one, a squared, that's this part, equals this part times the whole thing. We have an x and y. We can't do that. Okay, let's try z. If we want to figure out z, it would be z squared, because that's a leg. It's equivalent of a b, right? Equals this part of the hypotenuse, 9, times the whole thing. Again, we'd have 2 variables. So we can't use either of these to start off with. So we have to use this one. H squared is the 6. So I know 6 squared is going to equal the 2 parts of the hypotenuse, which is 9 times x. And then we solve for x. 6 squared is 36. Divide by 9, and we get x equals 4. Sweet. So now we can put that into our picture. Now this is important. How big is the entire hypotenuse? The entire hypotenuse is 9 plus 4, which is 13. So now we can use either of these 2 shortcuts, because c, we know c is now 13. Okay, so let's say a squared is the equivalent of y. Okay, so we know that the equation is going to be y squared, or this leg, is equal to this part of the hypotenuse, which is 4, times the whole hypotenuse, which is 13. So this is just geometric means. So 4 times 13 is 52, and then we have to take the square root of it and simplify. You guys know how to do that. Same thing over here. For the next equation, the last equation, we know that this is a leg, so z equals this part of the hypotenuse closest to it times the whole hypotenuse, which is 13. Sorry, z squared. So you do your math, you simplify the radical, and that's going to be what z equals. So this is a shortcut to Pythagorean theorem. And in this case, you could do Pythagorean theorem to figure out what z is, but then you're kind of stuck when it comes to y and x. Okay. Again, you can use Pythagorean theorem to check your work. If you are awesome enough to do that, you can always do that. Okay, so let's do the same thing. If you want to pause this and try it on your own, you're more than welcome to do that. For the rest of you guys who aren't sure what to do, I will keep playing it and follow along. So again, our 2 shortcuts are h squared equals the 2 parts of the hypotenuse, x and y. And then we have one leg equals the part of hypotenuse closest to it, which we'll call x, times the whole hypotenuse. And the other one is that the other leg is going to equal the part of the hypotenuse closest to it times the whole hypotenuse. Okay, so let's think about what we can do first here. If we try to figure out what the whole hypotenuse is, then we can use these 2 equations. So we need to know what c is in order to use that. Since u is in the hypotenuse, we can't use that one because we don't know what the other 2 legs are, and we'll have 2 variables. So for example, if I wanted to figure out what v is, it would be v equals 3 times the hypotenuse, which would be 3 plus u. 2 variables, can't solve it yet. Can't solve it yet. Okay, but so we're going to have to start with this one again. H is 9. It's the perpendicular piece. 9 squared is going to equal the 2 pieces of the hypotenuse, which would be 3 times u. And then you solve. 81 equals 3u. Divide by 3, and we get 27 equals u. Wait, yeah. So 27 equals u. Boom, done. Okay, and then you could use Pythagorean theorem if you wanted for this right triangle and figure out what W is. You could do Pythagorean theorem for this one and figure out what V is. You could totally do Pythagorean theorem if you want to. If you don't want to, though, you can use our shortcuts. So I'm going to show you how to use the shortcuts in case you want to figure them out. Let's say A is W. So this part of the leg squared is going to equal the part closest to it, 27, times, 27, times the whole hypotenuse, 27 plus 3 is 30. And then, so 27 times 30 is 810. And then you're going to have to square root it. Let's see, what can I divide 810 by? Well, I can divide it by 10. And I get 10 and 81. And then I know 81 is 9 and 9. So W is going to equal 9 radical 10, because 10 is just going to be 2 and 5. So it's not going to get me anywhere. Okay, so W equals 9 radical 10. So we figured out what this leg is. Now we need to figure out what this leg is. So this leg, V squared, is going to equal the side of the hypotenuse closest to it times the whole hypotenuse, which is 30. So we're going to get V equals the square root of 90, which is 9 and 10, 3 and 3. Again, 10 we can't break down, so V is going to equal 3 radical 10. In this case, if you don't want to use the shortcut, you don't have to. You can use Pythagorean theorem. Okay, why do we want to use this stuff? What is the purpose of all of this? Well, of course, there is some way for us to use it in real life. For instance, if you wanted to estimate the height of a Douglas fir, again, this is a dangerous situation. It's just like measuring the width of a volcano, right? I would not want you to go up and actually measure the height of a Douglas fir. So Jan positions herself, which really Jan doesn't look like a girl here, but that's okay. So let's say Jan is a girl, and she positions herself so that her lines of sight to the top and bottom of the tree, so top and bottom of the tree, form a 90-degree angle. So what that says is right here, this is 90 degrees, and this whole thing is a right triangle. And I'm running a little long, so I'm going to hurry up here. Her eyes are about 1.6 meters above the ground, which means she's about 1.6 meters tall, and she's standing 7.8 meters from the tree. And that makes a right angle, right? So what's the height of the tree to the nearest meter? So we want to figure out how tall that really the hypotenuse is. Okay, so again, our whole purpose is to figure out the height of this. So what we could do, we could do Pythagorean theorem and figure out how far this is, but why? We want to know how tall this one is, so we're going to have to use the shortcut. First one we're going to have to use is that a squared equals the two parts of the hypotenuse. Because we know this part is 1.6, and we'll call this part y, because we don't know what it is. All right, so h squared is always the perpendicular side, so 7.8 squared equals 1.6 times y. And then 7.8 squared is 60.84, and equals, and then you're going to have to divide by 1.6. So you're going to get that this part of the Douglas fir is 1.6, about 38.025 meters. That's this part, and you're not done because we want to know what the whole height is going to be. So to find the height, you're going to take y and add it to the 1.6. So add 1.6 to it, because that's how tall she is, and you're going to get 39.625 meters. That's how tall the Douglas fir tree is, and remember how long a meter stick is? So if you put 39 and a half almost meter sticks on top of each other, that's how long the Douglas fir tree is. Here's another question. See if you can answer this question, and we'll go over it first thing in the morning or in class. Thank you.